Video is going to explain the substitution method for solving a system of equations, two variables, two equations. And I'm going to go back and use notes that I used in a previous video, and I solved this system by the graphing method. I now want to solve the system by the substitution method. So with substitution is best to use when you can isolate one of the variables, when one of the variables would have a coefficient of +1. So here I've got y isolated in both equations. So by the reflexive property, y equals itself. So that's going to allow me to just take both of these equations and set them equal to each other in this particular system. And I'm going to solve for x. So in solving this, what I've done is temporarily eliminated y, or set y to the side. I should not have used the word eliminate. What I've temporarily done is just set y to the side, and I'm just going to focus on x, and I'm going to solve this for x. So when I subtract x from both sides and add 1 to both sides, it's easy to see that x equals +2, which is what I would have expected, because I've already solved this system by graphing, and I know that the value of x is 2. I'm just going to solve it now by a different method. So I know that x is 2, so in my ordered pair, I've got one of my solutions, and my job is to now find the value of y. So I would go back to either original equation, and I'm going to let x take on the value of 2. So if I just go back to the first equation, y equals 2 plus 1, therefore y is 3. And it doesn't matter which equation I go into, I will get the same answer both times. So the ordered pair that satisfies this system is the xy ordered pair 2, 3. So I have a two-variable system, I have two equations, and my solution is an xy ordered pair. So I need both the x and the y to represent the solution for this system. And what I would like to do is show you what it looks like algebraically when you have no solution, and then when you have infinite solutions. So here, once again, we've already graphed this in a previous video. We know that there's no single xy intersection point. So the lines are parallel, running parallel to each other. Two distinct y-intercepts, same slope. So they're climbing through the xy plane at the same rate, never intersecting each other. But let's see what happens when you try to solve this system algebraically. And once again, y has been isolated in both. So the reflexive property allows me to set y equal to itself. And then I just take the two equations and I set them equal to each other. So what I've done, I'm boxing this. What I've done is temporarily set y aside. I'm focusing on x. I'm solving a single variable equation. And now when I solve this, if I add 2x to both sides and subtract, well, when I just add 2x to both sides, what happens is the variable is going to leave the problem, and then what remains are two numbers that are not actually equal to each other. So when the variable sums out of the problem, if the two numbers that remain are not equal to each other, your conclusion here would be no solution. This is a no solution scenario. And then the third example, before we just go back to regular xy intersection, single systems that have an actual solution. So here, this is the system with infinite solutions, where you're actually just solving one for your graphing one line. Both original equations represent the same line, and I'm using my notes from the previous video. So I'm going to box this, and here I no longer have y isolated in both, but looking at the first equation, y is isolated in the first equation. So I'm simply going to take the isolated y expression, negative x plus 4, y equals negative x plus 4, and where y appears in the second equation, I'm going to let y become negative x plus 4. So here I'm going to copy this. This is my second equation. And in place of the y that's right here, I'm going to substitute this expression in, which is why the method is called substitution. And now, once again, I have this single variable equation. Y has been temporarily set aside. I'm focusing on x only. And when I solve this system, I see that the variables sum to 0. and what remains is a true statement. So when the variables sum to 0, if the numbers that are left over actually equal each other, then your conclusion would be this is a system with infinite solutions. And this is what we expected because we had already graphed it. We already knew what the outcome was. But I think it's important for you to see the 3 distinct outcomes. Here you have an x and a y value, which you find algebraically, and we're going to do some more of these together on the video. Here in the third example, the parallel line no solution example, when the variable sums to 0, the numbers that remain do not equal each other. So this is your cue that this is a no solution system. And then the third outcome, when the variables sum to 0, the numbers that remain are actually equal to each other. So the outcome would be an infinite solution system. And let's move to page number 6 in your notes. And let's do a few of these together just because this is the focus of the video. I just want to make sure that you're okay with the substitution method. So the first system is set up perfectly for substitution. You can see that in the second equation, the x has been isolated. X has a coefficient of +1. X is isolated. So I'm going to take the expression y plus 2, and I'm going to take this into the first equation. So here I've got 3x plus y equaling 6. And I'm going to slip in place for x. I'm going to slip in the expression y plus 2. So I now have taken the x and temporarily set it aside. I'm focusing on a single variable equation, which is something I can handle. So now solving this for y. And I see that the value of y is 0. So the value of y is 0. So the first member of my solution set is y is 0. I now need to find x. So I go back to either original equation. It doesn't matter which one I go back to. I'll use the second one. Easy enough. If y is 0 here, then it's easy to see that x is 2. So the solution to this system is the ordered pair 2, 0. And it will make both equations true. So if I test my ordered pair in the first equation, if x is 2, then I'm going to be left with 6 plus 0 equaling 6, and that's going to check. So this is the ordered pair that makes both equations true at the same time. If I were to graph the lines, this would be the point where they would intersect in the grid. Let's look at number 6 together. So in number 6, I need to analyze, and we'll have different methods for solving these in subsequent videos. But since the focus of this video is substitution, I need to solve this system by substitution. So as I'm analyzing, I see that in the second equation, y has a coefficient of +1. So y is going to be really easy to isolate in this second equation. So I'm going to take this, I'm going to add 3x to both sides. So it's really important that you stay organized and neat when you're solving these systems like this. So here I've taken the second equation, I'm isolating y. I'm now going to go into my first equation, and I've got 2x minus, and I'm going to slip that expression in, equaling -4. So I'm going to slip in 3x minus 9, and I put the parentheses there because this could be a place where you could make a careless mistake or a simple mistake with this. This is 2x minus y, so whatever y is, I need to make sure that I subtract everything that y represents. So that's why I chose to set it up like this. And now I'm going to clean this up and solve it. So I'm going to get -x equaling -13, therefore positive x equals +13. So the first member of my solution is x equaling +13, and my job now is to find the value of y. So here I'm finding x. So now my job is to find y. So I go back to either original equation, it doesn't matter which one I use, and I'll just go ahead and use the first equation. So if I let x become 13, it's going to be 26 minus y equals -4. Therefore, -y equals -30, which means positive y equals +30. So the solution to this system is the ordered pair X is 13, Y is 30. And once again, if I were to graph these, this would be their intersection point. So just to recap what I did, when I analyzed the system, the variable was not already isolated for me, so I had to decide, which variable was easiest to isolate and make that choice and do that. So I chose the second equation, I isolated the y, and then I take that into the first equation and I make a substitution. Wherever y would appear in the first equation, I substitute this expression in. This allows me to solve for x. I now have an equation just in one variable, in the x variable. Once I get a value for x, I go back to either original equation. I let x take on that number, and that allows me to solve for y. So two variables, two equations, and my ordered pair, two members, an x member and a y member. And let's do one more on the video before I move to the last example. And so analyzing here, I probably, the only logical thing to do would be to isolate the x in the first equation. So here x is going to equal 2y plus 5. And then I'm going to take that to the second equation. And I'm going to slip in 2y plus 5. So now I have an equation in a single variable. I'm going to solve this for y. And then that's going to tell me that y equals -7. So y is -7. And my job now is going to be to find x. So as I'm gathering my solution set, or my solution ordered pair, I know that one member is -7. So now my job is to find the value of x. I go back to either original equation, and let's see if I'll just go back to the first. So that's going to be -2 times -7 is +14, equaling 5. And when I subtract 14 from both sides, x is -9. So the solution to this system is the ordered pair. X is -9, y is -7. If you were to graph the both of the equations, they would intersect at this point. And the problem set that I've given you to work on is actually really easy. It's a little puzzle, so it should be easy for you all to do. And let's see, I'm just going to analyze quickly. Isolated. You don't have to really make too many choices here. In number 6, you're going to have to decide which variable to isolate. I would probably isolate the x by just adding y to both sides. And looking at these, I think that you all should be okay with this. Cautioning you on numbers 11 and 12. Now, number 11 would be easy enough to just isolate the x in the first equation. And in number 12, just make sure that when you isolate either x or y, it's your choice, just make sure that it has a positive sign. And the last thing I